where the audio test was.
Okay. So he's just done the audio and I think it was okay. Audio still good?
Yes.
Okay. So we're ready? Yes, I got a thumbs up. Okay, thank you very much. Thank you for being here after having spoken about the more expensive microfabrication approaches yesterday, where we may need a clean room facility. One of the challenges is that no one likes to pay a lot of money per chemical test. So making a test that is as cheap as we can is probably the biggest challenge in commercialization, because the more expensive the test is, the higher the barriers for uptake, and also the lower the profit margins that companies can make. So we looked yesterday at glass, which is a great material because chemists are really familiar with glass. It's inert, things don't really stick to glass. If our analytes like proteins are prone to sticking to glass, we know how to coat the glass so that it doesn't happen. But glass devices are really expensive to make or to buy, which makes it as a disposable not really an attractive avenue unless you're looking for gold in a gold mine where money doesn't really matter anymore. So people have been scratching the back of their heads. How can we actually make microfluidics cheaper? What is the cheapest possible substrate we can think of that we can do microfluidic tests on? So we want the applications at the point of need for both medical and environmental diagnostics, food safety, food security, as well as therapeutic drug monitoring. We have great microfluidic technologies. We've already talked through the whole toolbox, what we can do with microfluidics, but how can we do this while the devices are cheaper than $1 or about 50 rupees? And the answer is move away from all your polymers, use paper. Paper is around everywhere. Paper can be produced cheaply, and paper has got a very low environmental impact. So the idea was conceived that we could make microfluidic devices out of paper, and they're called, instead of the Miniaturized Total Analysis System, which was abbreviated as MicroTES, these devices are referred to as micropads, the miniaturized paper-based analytical device. The sizes of these are not as small as the microfluidics we've been talking about so far. So we're rather talking about millimeter scale than micrometer scale, but a lot of the fluidics happening in there is still at low Reynolds numbers, so we still are working on the laminar flow conditions. This is gives you an idea that once the idea was offered, again, we talked about PDMS. George Whitesides was the famous American scientist that came up with the idea of using PDMS for microfluidics. A couple of years later, he said, let's do paper. And you can see the world thought it was a really good idea, and we got significant growth in the use of paper for doing microfluidic testing. And in the meanwhile, one of the leaders in this field, Professor Chuck Henry from Colorado State University, he spun off a company for environmental sensing using micropads, using paper-based analytical devices. So the lower price per device actually does allow you to get to the market with a product that is based on microfluidics, but still affordable enough to use for environmental monitoring. So George Whitesides started in 2007 with the use of paper, which he patented using photoresist. We talked about photoresist yesterday, and they were the resins, the liquids that change their properties after exposure to UV light. What Whitesides did is that instead of using a silicon wafer to spin coat the glass on, he drenched paper in photoresist. So here we've got some ordinary chromatography paper. That's, I'm not sure if you've done chromatography when you were doing chemistry at high school, but you've got a bit of filter paper, you take a texture, you draw a little dot, you put it in a solvent, you allow the liquid front to wick up, and then your pen separates in the different components of the ink. This is that paper. Coffee filter paper would do the job as well. Instead of spin coating, which is a bit hard on paper, he just soaked it in photoresist. He just took a pipette and dripped it on. Realized that a wet bit of paper is hard to work with, so put it on a hot plate to evaporate most of the solvent out, equivalent to our standard processing with the soft bake. So now we've got a kind of a dry bit of paper that is soaked in a resin. Put it in under a UV light and use a photo mask to pattern the photoresist. After that, we can develop and rinse the device, which then means that after photolithography, there are some areas here where indicated in black, where the photoresist remains, and some areas where the photoresist wasn't cross-linked, where during the development process the photoresist was developed again. What the great thought of George Whitesides here is that most photoresists are organic materials. They are dissolved in organic solvents. They are not water soluble, which means that if they're penetrating a bit of paper, they form a hydrophobic barrier. We all know from the chromatography with the paper that paper very easily wets with water. But if we put an oil line, a hydrophobic barrier on there, then the water doesn't want to go there anymore, because the wicking process is driven by the hydrophilicity of the surface. You remember on the first day we talked about the wicking, and we saw that if we've got a well-wicking material or a capillary that is hydrophilic, and we've got water, we got a curved meniscus, and the liquid actually is dragged up because we have a like wall to our liquid. So here we create a dislike wall for our liquid. So we have an area where the paper is still hydrophilic because we have photolithographically removed the photoresist again, but we also have a hydrophobic barrier. And this hydrophobic barrier can stop the transport of water or the buffers or the reagents that are dissolved in it. So here are some examples of different devices that have been made using this approach, where you can see that you can make different channels using the resin. In this case, the wax barrier was made by a printer, so that we'll talk that as an alternative in a few slides. And you can see if you deposit a small amount of liquid in the paper, it gets constrained by the hydrophobic barriers that we've created using our microfabrication processes. So rather than the green dye here wetting everywhere, the green dye remains constrained to the area of the paper. Here we can see a barrier, a similar structure where some additional barriers have been put in place, and they can then be used to spatially localize the liquid. So we can see that if we then deposit the liquid in these little squares, it stays there. So we can confine the liquid to a very small area of our paper by simply putting a hydrophobic fence around it. It's like you want to keep cattle or sheep in a paddock, you put a fence around it. You want to keep your aqueous solution in your paper, you put a hydrophobic barrier around it. The last thing that has been done that we'll be talking about during this lecture is microfluidics, is that paper has got a great feature that most of the polymer and the glass devices don't have, and that is paper easily folds, which means that you can start off with a flat substrate, but you can then do some creative origami and you can fold your device together to have multi-layer functionality. So you can see in here, starting off with a flat substrate, you can actually fold the tab here over, you can tuck this under, and you've got a 3-layer device where in principle you could have embedded reagents and do a multi-step assay by starting off with a flat bit of paper, and when you want to conduct your assay in the field, you've got a small device that's like 5 by 5 centimeters that contains your different layers of functionality all stuck together. So paper microfluidics, I was about to say a decade ago, but it's probably more so 2 decades ago. That's how old I'm getting. It was really accessible for everybody because there were these things. Xerox sold a printer that was using a meltable wax as a laser printer. So it was just a cheap desktop laser printer that you could use in the office for printing, but their ink formulation was a wax. So you could make your design. Oh, that's my flower thing going on. That's my laser printer. So you could make the design with your favorite drawing package, which could be Photoshop or Adobe Illustrator. It could be a FreeCAD package. You can then just send it to your Xerox printer, put your print on the hot plate. The wax that was allowing you to print these beautiful shiny photographs would sink in the paper, creating the hydrophobic barrier all the way through. And then maybe if you had an engineer close by and you had an old inkjet printer, instead of using the CMYK colors, so your cartridges that you load into a normal inkjet printer, you could load them with your reagents, and you could selectively deposit reagents at different areas of your microfluidic device. Meaning you needed nothing more but a wax laser printer and an inkjet printer to get really advanced devices to do paper microfluidics on. Here we can see the surface, a print where the wax is still sitting on the surface. So we look from the side and we can see that only the wax is printed on the top. If we heat, the wax melts and wicks down into the paper below where it has been printed. We have a problem though. Around 2015, Xerox decided that other inks are cheaper. So they stopped selling the wax printer, which has been a big blow for anyone doing paper microfluidics. There's been for a couple of years a lively trade in second-hand printers, but currently people are looking for other ways, use the photolithographic ways, or instead of a wax barrier, use the xerography that we've seen yesterday with the cutters to actually, instead of a wax barrier, just have stop the fluidic conductivity by making a little slit, because Xerox didn't think it was worthwhile supporting the microfluidics, keeping their wax-based printer on the market. So a lot of literature that you'll find written up to around 2016, 2017, people really say it's so easily accessible because you can just get a printer at any stationery store and you're good to go. Yeah, with Xerox decision that has actually really hurt the community and made it less accessible. So be aware if you're reading that information. The Xerox printer is no more and they become a really sought after device on the second-hand market because there's a lot of PhD students desperate to finish their PhD that have a broken wax printer. So how does it all work? On the first day we already talked about the importance of wettability, where if we've got a hydrophobic coating, in this case on a glass slide, we get a droplet to bead up. It doesn't like to wet the surface. Whereas if we've got a hydrophilic surface, the droplets go flat, and we will, if it's, will be able to wet this material with the aqueous solution. Here is a nice illustration of what happens if you just put a drop of an aqueous solution, in this case an ink, on a bit of paper. And it just spreads everywhere. So with the wax, we can create barriers to control that fluidic transport. And there has now been, people are creative, a whole range of different ways that these barriers can be made. So we started off with white sides using photolithography. Were people that using different kinds of 3D printers to deposit hydrophobic barriers. Wax techniques, so there's the printers, but you can also use, just commercially buy different waxes to deposit. You could deposit wax-like materials using screen printing processes, which allows you to make repeatable processes. There are some permanent markers that are hydrophobic. You can formulate your own resins for ink. People have tried stamping. Eyeliner is very hydrophobic, so you could use eyeliner for the same purpose. You can, instead of making the hydrophobic barriers from wax, you can just use a paper cutter with xerography to remove a small part of the paper and that way stop the wicking process. Salt gels can be created to create a hydrophobic barrier, some glues and laser cutting. So there is a wide range of different approaches of making these paper microfluidic devices. And here you can see a nice example. We'll go through some more during this lecture. But you can see how elegant the use of paper microfluidics can be. Here the example on the left is a paper microfluidic device where in the preparation coulometric reagents have been deposited for copper, nickel and iron. So these were deposited in the outer circles here and then allowed to dry. When a sample gets deposited in the center, the sample wicks up to the corners because the hydrophobic barriers that is contained within the hydrophobic barriers, and that way you can see the coulometric change if the analyte is present. We can also do that with different amounts of reagents. If we've got control of the volume of reagents we're depositing, then the color intensity becomes an indication for our concentration. So here we're looking only at nitrite, but you can see that the intensity of pink changes around the circle. So this is allows you to determine the concentration of nitrite, so not just the present, based on the intensity of the pink color of the grease reagent. So creating small hydrophobic barriers. We can do it, we can make patterns or we can make shapes. We can make shapes by cutting, using a razor blade, embossing, punching it out, or laser etching, using a laser to cut. Like we talked about laser ablation of microchannels, you can also use a laser to cut paper. We can also use patterning techniques where photolithography, like George Whiteside started off with, printing, the wax-based printer, some inkjet toner or screen printing have been developed as well, but really the Xerox printer was absolutely the star of the show and then is no longer available. We can work with some wet etching as well, or selective surface treatment for putting a mask on and using a plasma that we've seen before in making the surface area of PDMS hydrophilic. We can also use that on our paper or paper-like substrates to make selective areas more hydrophilic than others. So that is the sad story about our printer, but you can see that the printer had very good performance. So what's been done here is that in Photoshop at 2400 dpi, a line width can be realized that is 30 micron. But then it still needs to be printed. If you use a standard inkjet printer here, an average off-the-shelf Epson printer, you can see that actually 100 micron lines can be printed. And with the famous Xerox printer, is 120, even though if you put them really close together, they will flow together a little bit, which is probably one of the reasons that Xerox moved away, because the wet wax maybe wicked into the paper a little bit too well. So we can make different line widths using PowerPoint, and you can see they could be replicated onto the paper using the print process. So all techniques relying on the hydrophobic barrier risk that they lose resolution because of the wicking of the material. For having a good analytical assay, you want speed, so you want a really coarse, porous paper. And I hope we'll be doing a hands-on session later this morning. And I hope we have some different kinds of filter paper with different coarseness, because you can see that there are some papers that will wick faster than others, depending on the pore size of the paper. But a good paper for wicking also means that as soon as you deposit your ink or your hydrophobic barrier, that's going to wick and spread as well. So you need to compromise at some point between the resolution that you can achieve with your manufacturing method and the speed that you can realize with your assay. They are kind of two different parameters, and there's an optimum there somewhere. So some critics have said micropet sounds all fancy, but it's actually nothing more than a pregnancy test. And that's not quite true. A lateral flow assay or a pregnancy test is indeed a very primitive example of a paper microfluidic device. At this point, I want to let you know that any paper-like material is considered paper microfluidics. So nitrocellulose membranes, if you put a barrier on, we still put it on the paper microfluidics umbrella. A lateral flow assay, like pregnancy tests, but also COVID tests, are indeed using the wicking to transport your sample and some reagents that you've added with your sample preparation. It's my wrong button again. It wicks up. We get our test line that if our analyte is present, the analyte binds to the antibodies here as well as to the gold nanoparticles. And there's the control line to demonstrate that the test actually worked all appropriately, so that is control. So it is similar in terms of material, but a micropet can get a lot more complex. I told you about the folding, so we can go from 2-dimensional to 3-dimensional. The fluidic control, by using the geometries of our wax barriers, we can control the flow. We can either facilitate mixing or we can prevent mixing, because we've learned a lot studying the fluid dynamics that I bored you with last week. We can do some separations, either by having selectivity as an additional layer coated onto the paper for chromatographic separations, or based on other properties, including if we start separating particles. People have also done electrophoretic separations by adding electrodes to the paper microfluidic devices. And in micropets, we have access to a much broader range of detection technologies. We're not only looking at the beautiful purple lines of the gold nanoparticles that are sitting there. We can use different colorimetric reagents that are known and have been known for decades to be selective for certain analytes. But with some carbon pencils, we can draw electrodes. So we can do electrochemical detection. We can use fluorescence readout by having an excitation and an emission filter. So we've got access to a much broader range of detection approaches when we're talking about a micropet instead of a simple lateral flow assay. The materials, I already said that any cellulose, nitrocellulose has very strong covalent interactions within it, negative surface charge. Another option are chitosan-based papers, and the interesting there that it has a primary amine, which means that it's got positive surface charge, and that allows for covalent attachments from another series of reagents. Local surface modification can be used to stabilize detection zones or immobilize reagents. So we have a wide variety of different membranes that all fit together under the umbrella of micropets. So with the lateral flow assay, we had one flow path, one analyte test line, one analyte control line. That is how creative life can get. With a micropet, we can direct the flow, and that means that we can split the sample radially. Here we've got an example of a device where we've got a couple of different reservoirs that each contain embedded reagents specific for different analytes. So we load a single sample that wicks up and goes into all these branches. And we can see that we've got controls here to indicate that actually, yes, all the areas have properly wicked. And we've got nickel, chromium 4, copper, mercury, and and then a reagent that is selective for a group of different metals. So we can see if those analytes are present. We get, depending on the analytes present in our sample, we get a different color profile in our device. Here we've got another example, again looking at quantitation, where we've got detection of copper using gold nanoparticles, where we can see that 7 has got the highest intensity, 8 the lowest, and we can see, or 8 is probably our control, 1 is the lowest, and we can see that we can calibrate our device by having increasing amounts of reagents already embedded before we do the assay in each of the reservoirs. So in the lateral flow, we had one flow path. In the 2D ones that we looked at the previous slide, we can go radially. In a 3D micropad, we actually introduce a vertical component. Transformations can be facilitated simply by folding, bending or twisting the paper to create multi-layer devices. This is attractive if you want to do a multi-step assay. It provides you for multiple regions to add different reagents or look at different analytes, and it reduces the sample loss during the reagent process. I've got 2 examples on how these folded microfluidics work. If you struggle to follow, the easiest would probably be to just get a bit of paper, cut it in the same shape, have it in your hands and just do the folding yourself. Because sometimes it's hard to imagine how things are being folded together by just looking at a stationary slide. But if you've got it in front of you, you can play with it, it makes it a lot easier. We probably all have at high school started off making with a flat sheet of paper and having to make a cube and then having to put the dots on the right areas to make this cube into a dice, where you've got the 1 opposite the 6, and it requires a lot of thinking through where you need to put the 1, where you need to put the 2 and the 5, the 1 and the 6, to know where they're going to end up in your ultimate cube. Working with a foldable paper microfluidic device requires the same kind of visual thinking. So some people have no problem doing it. Some people need to fold the cube together, put the dots on lightly with a pencil, fold it open again, do the drawing, and then put it back together again. There is no right or wrong way of doing it. But here we've got a device that's got 4 different functional areas. If we fold this over the line that I indicate here, it means that the dot that we've got located here ends up in the middle of this channel. And we have these 2 channels connecting the 2 sides of the other square. So we fold this one in half and then we fold it again, which then means that we get a different ways of connecting our reservoirs through the fluidic pathways from a single inlet to multiple outlets. We can also fold it only one way, so here we will be, after folding, creating a fluidic connecting path between this reservoir and this one here, when that folds over that one. And here we can see again, we've got a very different structure where this reservoir can get folded to connect with this fluidic line, which then gets folded over to be sitting on top of those, and then the 4 reservoirs here are connected to the outlets of the channels. So there's inward folding, T-folding. However people have done origami, you will be able to do it. I like the Z-folding here, where you've got 2 half channels when you're making it, which makes it very easy when you're putting in reagent because you can't get any contamination. With the Z-fold, after you've put 2 reagents in, you can actually make it into a single device by using or into a single channel, as you can see here, using the Z-fold. So this one then lays on top of the other one. This here is a more complex version where we've got different areas. The purple ones are there to collect excess liquids, and they are called the waste steps. We've got a fluidic structure here, which is called a reagent, which distributes a common reagent used in all the assays. And we've got the tab here where actually our sample is deposited and our assay takes place. So we've got 4 different microzones here that each have an antibody to bind a different analyte. We've got waste tabs and filter tabs. The filter tab will be here added on top. The reagent tab, the 4 branches here. So the reagent comes in here, the reagent is peroxide, and that can be delivered to each of the immunozones when needed. And I think my next slide has got the folding process, yes. So we work with this whole assay, so we load all the reagents, preload the dried-in reagents, and the assay will be conducted by pipetting at later. So both the waste tabs are, once they're used, you can pull them off. We have some separation to make sure cross-contamination with these additional blotting lines. And the immunozones are simply using a countersand coating on the paper to bind the antibodies, as we know from antibody binding, for example, with pregnancy tests. So there's a lot of know-how already there, how to make these, attach these coulometric zones to paper-like substrates. Here we've got the assay that I already referred to. So fold over the filter tab, add the blood and allow the blood cells to be separated by the filter and only leave the liquid over on there. Once that's done, it can be removed. So you can just see the arrow here, and the nice thing about paper is you can just tear it away so it's out of the way. Then we can add the washing buffer. After that, we can remove another area where our waste products end up. We can add the reagents. Zapping there. We can remove another waste step, and then ultimately we can add our peroxide solution to all our 4 reservoirs, because that will drive our chemiluminescence reaction that we use as readout. On this slide, it shows you the chemiluminescence intensity for 4 different analytes that were deposited onto their respective graphs. So we have a multiplex sandwich chemiluminescence assay on a tiny bit of paper, controlled in a manner that if we can follow add reagent A here, tear the tab off, add reagent B, it is not really complex to operate these devices, and we can get good sensitivity for a number of different proteins that we could measure in the blood. So a bit of paper with very complex geometries and a lot of thinking in how to fold it all together, but we can do a rather complex assay on a simple sheet of paper. To increase speed, people have realized that the paper actually slows down the process. So people have also started making paper-based microfluidic devices where the actual microchannel sitting in between the wax layer is a void. So you almost start using your paper as a polymer substrate, but then cheaper. So for high-speed applications, hollow micropits have been developed. And here you can see that in one of these hollow paper-like devices, we have laminar flow just like we expect on any polymer device that we've seen so far. So we can see a yellow dye and a blue dye coming together. Laminar flow means that we don't have any mixing. If we've got a fluidic splitter here, we can see that we can split the yellow and the blue dyes and then recombine them again. And with laminar flow, we can do so without mixing. So on these devices, using a spacer between 2 bits of paper that have been made hydrophilic using a wax, we can use that as well as a microfluidic substrate. and we can use that. So if you are an analytical chemist, you may have heard about the flow injection analysis, where we've got typically our analyte that is being mixed with a reagent, and there's a carrier that pushes that sequence along a detector. This is a micropipette version of a flow injection analysis, looking at different number of layers of paper in order to get the reaction speed, and using an electrochemical detector we can actually do assays by flow injection analysis using ordered reagent delivery in our micropipettes. So, microfluidic control. It has been a challenge in our normal devices, and that is not really different with our micropipettes. If we want to do assays, we want to not have everything randomly mixing. We want antibodies and antigens to incubate for a minute. So we want to have a control on what fluid goes where at what time. One of the ways that it can be achieved is by pretty much sliding the test strip to contact your reagents at a certain order. So this is a hydrophobic test strip other than the small area that is left in white here. Here we've got a small device where we've got reagents and buffers. We can pull this strip through the device. As long as this reservoir is in contact with the hydrophobically coated paper, nothing happens. The aqueous reagent does not want to enter. But if we pull this strip through, there will be a point that this hydrophilic spot is in contact, which means that it will wick in. We can then, so this reagent wicks through and may end up on a pad on the other side to not make a mess. If we pull it further, then the second reagent will enter as well. Again, we pull it a little bit further and we can use the buffer to wash, and then we can add a substrate to do detection. So by simply pulling a strip that only has got one hydrophilic zone past a couple of chambers, we can control the time that an assay is taking place at. We can do some manual valving as well by moving the paper around. So here we can see the first reagent goes to the middle, move it around, you can pipette the second reagent, and that way you can do a sandwich assay by adding one reagent to another, having one part of the mass that can be moved, whereas the other is stationary, so you can deposit one reagent after another to the same zone. We can also introduce soluble barriers or dissolvable barriers, which means that we can delay the rate at which a sample can wick. So here we've got a microfluidic device with a flow splitter that goes into two. In this instance, it hasn't been made with a wax printer, but it has simply been made by a laser cutter. So we've got very thin strips of paper here. We can see that if we get to the intersection, the water will wick at the same rate. But if we introduce some sugar solution here dried up, then the wicking will be inhibited by the dissolution of the sugar. So you can see that where the sugar barrier was put in place, our liquid is being delayed. So whereas from the intersection, they enter the intersection at the same rate, we can see that the right hand is delayed compared to the left hand because a sugar-based reagent was introduced, and the aqueous phase will only pass through when the crystallized sugar has been dissolved. So nice way to introduce a small delay. Chemists are chemists, and chemists like playing around with reagents. So what's been done here is use a surfactant to dissolve a thin wax barrier. So rather than the water just dissolving the sugar, here we've got two different reagents. The green one doesn't have any surfactant, just goes anywhere. The blue one does have a surfactant in there, and over time, initially we can just fill them one after another, but over time the surfactant present in the blue reagents dissolves that wax barrier and allows for contact between our blue reagent and our green one. So by fine-tuning the thickness of the barrier and the concentration of the surfactant, you create a way to sequentially add reagents and that way enhance the complexity of the chemical assay you can be conducting on the paper substrate. Engineers wouldn't be engineers if there's at a certain point not a kind of robotics being involved. Here we've got a little on switch that can have a mechanical actuator that can bring channel A in contact with channel B. So only when we've got contact between two bits of paper, and that may be something for you to try during our second session this morning as well. If you want to transfer liquid from one bit of paper to another, it only happens when they're brought in contact. That's what the switch has been doing here. Switch is off, it's not. We can make life more complex when there's another third channel going in the plane of the screen, and that means that we now have a contact between channel A and B. If we move it up, we get in contact with the top channel here, with channel C. So by switching the position of channel A or paper strip A, we can either be in contact with the bit of paper that is in plane or with the one that sits on top. So we can switch from transporting our liquids in one direction or another, having a little mechanical element in our paper microfluidic device. This is a very creative way to pull apart a separation. So what has been done here is that paper has been folded together, and in the transparent dots there is hydrogel. We know that electrophoretic separations, we have different migration velocities in an electric field, and gel electrophoresis can be used to separate different compounds. If we apply our potential difference, we can allow our analytes to be moving through, but our fast analytes will be getting to the top faster than our slow ones. So we can have our separation taking place for a little bit when we've got our device folded together. If we open it up, we can actually see the different stages of the separation and access them separately, which is something that with a normal CE separation or a chromatography column, it is going to be very hard to stop and freeze and take a hacksaw to chop off a bit of your separation. But with these paper devices, when folded together, you can do the separation. When you think you're done, you can fold it open and you can selectively get your analyte plugs that you want to have. And here we can see a device that we use some electrophoresis. Here we've got green will be fluorescein, so an anionic dye. Red is rhodamine, which is a cationic dye. If we apply an electric field, we can have a joint sample coming in and electrophoretically separate them. This is a paper where isotachophoresis has been done on a paper microfluidic device, again concentrating DNA from a very dilute sample into a highly concentrated zone using paper as a support. And here we can see that these separations can also be combined with an electrochemical detector that either can be made using thin gold strips attached to the paper, or you can use a pencil, because carbon is a conducting material as well. So if you've got a pencil that's got carbon in there, graphite, you can actually create an electrode that way. So we can do a chromatographic separation using the interaction with the paper, and then do electrochemical detection at the end of the micropad, connecting your potentiostat to electrodes that you've either printed or deposited on. We've just looked at the electrophoretic separations of proteins. We talked about that in detail. That's why they all looked very small. So I had an overview slide and then all of them bigger. So here we've got the positive potential and the ground, where we get a sample coming in. If the sample contains some fluorescein, the fluorescein is deviated to the top towards the positive electrode, whereas the cationic rhodamine is being separated down. So we can separate up. So it was, the green was electrofluor, which is also an anion, and rubipi, which is a cation. So different dyes, but still the same charges. Another way of separating and concentrating molecules is ion concentration polarization, where an ion selective membrane can be used to selectively remove all the, in this case, cations. So Nephion is a cation exchanger. It allows for the passing of sodium, but not any other ions, which means that we get a depletion zone being created. And these ion depletion zones get a really high field strength, which allows for the concentration of analytes. So here we can see a paper microfluidic device where the Nephion membrane creates an ion concentration polarization zone, which allows for the significant concentration of our analyte. Here you can see the ion concentration polarization happening, and we can detect really low or low micromolar numbers, concentrations of our target analyte in our devices. This is Moran's paper microfluidic device, where for isotechophoresis, so very shallow channels were created here using double-sided print. So using the double-sided print, you could decrease the thickness of the paper by also having the print on the back side wicking into the paper. So you only use a part of the paper. And if you remember in electrophoresis, the resolution or in the speed at which the isotechophoresis zone will establish depends on the potential difference that we can apply. If we create a shallower channel, the resistance will be higher, the electrical resistance, which means we can apply a higher potential difference. What was done in this device is that 30 microliter of sample was deposited at one of these circles, and a 1,000-fold concentration could be achieved in isotechophoresis for 6 minutes. For anyone that's done any sample preparation, solid phase extraction for HPLC, you're typically glad if you get a 50 or 100-fold. A 1,000-fold concentration factor of your analyte is really an impressive achievement. And if you can do that on a simple bit of paper, that makes it even more interesting. So, happened a while ago, but a nice result. So for the detection, we have a range of different options. Most obviously is the colorimetry, particularly because for a lot of metals, we actually already know the colorimetric reagents. We can add detectors for electrochemical detection, either selective with special coatings or just looking at the oxidation and reduction potentials. We can add some optics to do either fluorescence or luminescence detection using a photon counter or photon diode. You can also use them for Raman spectroscopy, so see what the analytes are that are present. We can have both qualitative and quantitative assays. And the advantage of colorimetric is that we get a simple visual readout, which means that if we want to do in-field testing, the amount of equipment that we need for evaluation is not as significant. If you're interested in a particular application, in chemical reviews there was a really nice review looking at the different detection methods that have been demonstrated on micropads, what their advantages and their disadvantages are. So if you've got a specific application in mind, this table provides you with a really fast way of selecting the right detection approach for your situation. And it also provides access to references where people have already done that, where you can take some inspiration from. So this was the introduction to the micropads. After our cup of tea, we can walk to the chemistry department. I've got some crayons in my bag. Professor Malik and Jetty will have prepared some hot plates for us and some filter paper, and we can start making some microfluidic devices. I think it's the easiest, as I don't know if I have a projector there, to already introduce you to the tutorial here. and then we can just go and do it. So this is some examples of what people have done using crayons and the fluidics that they've created. So created hydrophobic barriers, and in this case worked with red and yellow food dyes, looking at different structures and see how they could make them connect using hydrophobic barriers. These are structures where you can actually play with, that have been made by other people with crayons, using a reservoir for a red dye and a yellow dye, and then see how you could fluidically get them to meet and mix in a centralized microchannel. You can see if heart shapes feel any better or worse than normal circles. And if you're unsure what to do, this movie shows, and I'll do, there's a very long introduction, and the sound was not very informative. So I'll skip here if it allows me to skip to a certain time in the timeline where we do get to the paper fluidics. So here we can see some experiments that during COVID have been done on some filter paper with some food dyes. You can see, you can create a whole range of different structures, any shape that you want. You can put little barriers in to see if you can enhance mixing or stop mixing, circular reservoirs, non-circular reservoirs. And now they're going into, if you want to quantify detection, you could either do it with the bare eye, but if you want to get a more numerical value out, there is image analysis software that you can make a photo with your phone to do that. So what you'd need is some crayons, some paper, maybe a template, but we're now just going to play, and some food dyes. So that is what will be available in the chemistry department for us. If you want to be really precise, you could first use a pen to make your design. Otherwise, feel free to start using the crayons directly. You can put the structures in there. In this instance, they've used the crayon. We will be using a hot plate, but anything that heats it up will work. So they put it in an oven at 120 degrees. We'll be resting our device for 5 or 10 seconds on a hot plate, allowing the wax to melt through. We'll have some food dyes, and we can just add little droplets. I think it will show here, yeah. So add the droplets of our food dyes, and then just watch what happens and see if our hydrophobic barriers are functional or if we've got little leaks. You can see that we've got laminar flow, but we've got some deviation where we've got a preferred flow of the blue of the other. So the intent is for you to have a little bit of play, see what you can do with microfluidics, see if you can make some designs that do what you like. We're not going to go into all the image analysis here, so this is all part of the video that we don't need to look at. So it is just going to be, have some fun in the lab, make some paper microfluidic devices, see how good these wax barriers are actually, see if you can develop a small experiment, change length, see how fast things move depending on the channel widths. And I think the 2-hour interval that we've got for it is perhaps a bit long. I think with the size of the group, we'll probably be able to finish early for an early lunch. So I hope our tea is ready, and then we're going to do some paper microfluidics in the chemistry department. Thank you very much. And any questions, as always, just come and ask. So we'll be back here after lunch.